My name is Roy Simpson, and I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another proof in my series for differential calculus, and this proof is going to cover the sum and difference rules for derivatives. So the derivative of the sum or difference of functions is the sum or difference of their derivatives. That's basically a summation of what the theorem states. That also supposes that f and g are differentiable functions. So let's go ahead and write down some prerequisite knowledge here. As with most of our proofs so far in calculus, when we're dealing with derivatives, you have to be very familiar with limits and then the limit definition of a derivative, without which we could not do any derivative. So that's the reason why we constantly refer back to the limit definition of a derivative. Let's go ahead and start the proof. We're first going to suppose that f and g are differentiable functions. And this is because we have to. The proof is telling us that it relies upon the fact that they're differentiable functions. So whenever you start a proof in mathematics, you always want to write down what you're allowed to suppose. So the supposition here is if f and g are differentiable functions. Great. So we get to suppose that. Then with that supposition, we can then do a little more mathematics behind the scene, or logical proof behind the scene. We're going to go ahead and let capital F of x be a summation function. So f of x plus g of x. And the proof for f of x minus g of x will look just like this. So I'm only going to do the summation, and I'll leave it to you to extrapolate the difference theorem. Then the derivative of f at x is equal to the limit as h approaches 0 of capital F of x plus h minus capital F of x all over h. And of course, if we were to plug in to this limit as h approaches 0, x plus h into our capital F function, we would get little f of x plus h plus little g of x plus h, and then minus, and now we're going to subtract off that function evaluated at x, so minus f of x minus g of x. Remember, we're subtracting both those sub-functions. And that's all over h. But we get to use something that we supposed here. We supposed f and g are both differentiable functions, which implies that if we write this as the limit as h approaches 0 of, I'll put a big brace on here, f of x plus h minus f of x, so I'm just reordering the numerator, plus g of x plus h minus g of x, and write that over h. You could see that we could split this fraction, and this is a warning that I give to a lot of my students, is that you cannot split a limit unless the split, though basically both limits you split it into, exist. So I'm going to cross my fingers right now and hope that I can break this limit up. First, I'll go ahead and write this as a sum of two fractions, like so, and then I will go ahead and break the limit. And remember, as I was saying, you can only break a limit if what you break it into exists and is finite. However, in this case, both these limits exist because we stated early on that f and g are differentiable functions. So that means that this first limit is actually equal to little f prime of x, and that second limit is actually equal to little g prime of x. Well, that is it. That is actually the proof. So we have just said that, remember, capital F prime of x, which is actually the derivative with respect to x of f of x plus g of x, is now stated to be equal to f prime of x plus g prime of x. That is exactly what we wanted to prove. Not so bad as far as proofs go.